Hi. In this video, we're going to be making an embedding that is purely based on count vectors of n-grams of words. And it deserves mentioning that what I'm going to do in this video is a bit of a theoretical curiosity that I came up with. It's not something that I recommend you use in practice, but it is a cute result that demonstrates something interesting about subword embeddings as well as these n-grams. So as a reminder, if I have the word university, what I could do is I could convert that into sets of n-grams using a count vectorizer. So the first thing that would happen is I would get these subtokens like uni, NIV, IVE, and let's say that I go all the way up until 5 grams, so I would also have something like UNIVE that would look something like this. And the count vector representation would eventually be this sparse array. And the array would have many zeros, but it would have a couple of ones, basically indicating when we do see a certain n-gram. So this is just a representation that is sparse, that represents the word university. But what you can imagine is that I don't just do this for the word university. What I can do is I can do this for, let's say, the top 10,000 words in the English language. And if I were to do that, I wouldn't end up with just one single array. I would end up with something that resembles a matrix a bit more. And this matrix too would have way more zeros than ones. And the idea here would be that every row represents a word. So this might be apple, and this might be zoo at the bottom. Now these count vectors are sparse, and that's fine, but let's say that I'm interested in having them to be dense. What I want to do is I want to reduce the dimensionality of this big sparse matrix into something that is maybe just a little bit more dense. So the idea is to go from the matrix that you see here on the left to something that's a little bit more like the matrix that you see here on the right. A potential benefit of having this over here is that you can calculate different distances a little bit more effectively. But before we get there, we have to think about how we're going to get these dense representations. Now the idea here is that we're going to have to apply some sort of dimensionality reduction technique, such that what we end up with here is a dense array per word. And when you think about dimensionality reduction techniques, you might have heard of something called principal component analysis, the abbreviation for which is PCA. However, the downside of PCA, at least the implementation in scikit-learn, is that you have to pass it a dense matrix as input if you would like that to work. So what I'm going to do is I'm not going to be using PCA for this, but a different technique that's very similar called SVD. For our intents and purposes, it pretty much does the same thing, but the one detail that's worth to mention is that the SVD implementation in scikit-learn allows for sparse input. But the idea is going to be that I am now generating a embedding of sorts, because these are arrays of numbers that represent words, and the question is what property this embedding will have. And the reason why I think it's interesting to have a look at the properties here is because these words are not trained on how they're used in the language. We are just looking at the characters and how those are used inside of the word. So then the question is, what sort of properties can we expect here? To answer that question, what I've gone ahead and done is I have implemented the approach that I just explained into what lies in this count vector language class. What the count vector language will do is it will first apply a count vectorizer. You can see the setting for that over here. We have an n-gram range here, so we're going to be taking the 1 gram, bigram, and trigrams. And then we're going to apply SVD, and we'll end up with vectors of size 20. And I'm learning this pattern from this word list that I downloaded up front, and it contains the 10,000 most frequently used words in the English language. One thing of pre-processing that I am doing to keep things simple, there are words in here like American, and I think having a capitalization here isn't necessarily a bad thing, but just to keep everything as equal as possible, I am making all of these words lowercased before doing anything with n-grams. So given this trained count vector language backend, you can wonder, well, what are the most similar words? So what I could do is I could say, well, given the word hello, what does this language think are the most similar words so far? And let's have a look. Now note that I'm not doing cosine distance here, I'm doing Euclidean distance. But we notice that if I give it hello, I tend to see a lot of words that have double L. So that's interesting, but let's now also have a look at a different word, the word add. Now the interesting thing with the word add is that the word add also appears in our corpus. So that's a word that we also train on. And that is why we get this as our first result. The distance is pretty much 0. But looking at add over here, sure, one pattern that I see is that the letter D and the letter A tends to appear here and there. But if I were to compare this to what I saw before, notice how all of these words tend to be 4 or 5 letters, whereas all of these words tend to be 3 or 4. So it's also picking up that it's a shorter word. Let's compare this to a very long word. And again, what we see is that because administration is in our training data, we get this as a first result. But also notice here that we get relatively long words back, with the exception of words that just overlap. So this Asian over here, you also have that in station and in nation. Now, I don't know about you, but one thing that I found quite interesting when I looked at this is that it seems like we have an embedding that is able to capture Levensstein distance. Now, Levensthein distance, in the case that you're not familiar, is this string metric. It can compare how different two strings are. And the way that Levensthein distance works is you either get to delete a letter, you get to insert a letter, or you get to change a letter. And each of these operations counts as one measurement of distance. So if I take the example that is on Wikipedia, if I have the word kitten, and if I have the word sitting, then I would have a Levensthein distance of 3. Because how can I get from kitten to sitting? Well, I can replace the K here with an S, I can replace the E here with an I, and then at the end I can add a G. And that will be the minimum number of steps that I would need to get from kitten to sitting using these 3 operations. And I do think it's quite interesting that I seem to have an embedding here that captures very similar information. If you think about the information that is being used to construct these embeddings, it doesn't occur to me as odd, but it is something that is interesting. So this made me wonder, is there a correlation between the Euclidean distance that I have in this embedding and this Levensthein distance? Because if those two things correlate, I would argue that's quite interesting and a cute result. So what I've done is I've gone to Google and I found myself an implementation of Levensthein distance. And what I'm doing in the code below here is I am taking 2 random words from my word list, I'm doing that over here, and then I'm going to be calculating the Euclidean distance from my word embeddings. And what I'm going to be doing is I'm going to be calculating this Levensthein distance. And I'm just going to be doing that for random words. And the question is, if I do that for a whole bunch of random words, can I see a correlation between the Euclidean distance and the Levensthein distance? And it turns out, yeah, you can. It's not a perfect one-to-one mapping, but one thing that I have seen in this embedded space is that we do indeed capture something that's reasonably similar to Levensthein distance. And that I found to be a relatively cute phenomenon. Now, as a final remark, what I've just shown you isn't that special if you think about where our information comes from. What we've done is we've taken this dense matrix, and we've shown that it indeed correlates with Levenstein distance, but that's of course because this count vector sparse matrix also resembles which characters appear in a word. So you could also argue it the other way around. It will be really strange if whatever we learn from these count vectors doesn't correlate with these Levenshtein distances. That said, I do think it's reasonably nice to have access to some sort of an embedding that captures how characters are used and little else. The only thing that these dense vectors contain are the order in which characters appear in the word. And this, I would argue, makes them fairly easy to reason about. They are trained for one thing, and that's the only thing that they can contain. But if I start thinking about what word embeddings might learn from text in general, then I have to sit down and think what all the different patterns are that these word embeddings might capture. So in the next couple of videos, I will explore this theme, because there are some things that some of these general word embeddings do that aren't necessarily a good thing.